Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the good stuff. This is the Sky and Telescope series. And I am super happy to have Sky and Telescope author Shivani Bhandari with us today. Hey, Shivani.
Hi everyone. Hi Frank. How is it? How is it going?
I am doing super well on this September 8th of 2022 as we shoot this. And summer is in full bloom in Phoenix. Getting a little rain, actually. This is when we get our rains. And Shivani, where are you located at?
So I am in this very pretty Dutch countryside, 2 hours away from Amsterdam. It's a
Cool.
very pretty small town called Meppel. So I work in Astron, which is like a half an hour drive from here. So Astron is basically in the middle of nowhere, and it's a very beautiful national park. So yeah, I'm just having all sorts of excitement and getting to know the Dutch culture and food. Yeah, so it's really awesome.
Do you speak Dutch? Have you picked up any Dutch?
Just so that I can recognize what's on the menu.
Oh, there we go. Water, please. Very cool.
Yeah.
Very cool. So I take it then. So you do research in fast radio bursts.
Yes.
And so I'm curious, how did you decide or get recruited to do a Sky and Telescope article?
Yeah, so it's an interesting story. So when I was doing my research and we had a really great publication about like actually localizing an FRB to a non-repeating FRB to its host galaxy, and that led me up like that gave me a lot of opportunities to actually do outreach. So we were just like going there and doing interviews, talking to public, and I thought I really like doing it. So I would really love to write an article about, because this field is so fast evolving, and for general audience it's so hard to catch up, because it's only hard for me. If I write a paper, I have to keep changing my introduction like every 2 weeks. So I thought it will be a good idea to just like get to give people the chance to actually read in a very briefly, in a very layman way, as to what's going on in the field, because it's a very hot topic and very exciting. So I got approached by the editor of Sky and Telescope asking me if I'll be interested to do this article, and I was like, yes, absolutely. And that's how yeah.
That would be Camille.
Yeah, that was
Okay.
Camille. Yeah.
Very cool. Very cool. Yeah, and so let's go there. So FRBs is a very it's a relatively new topic. It's very fast moving. And how might this is Sky and Telescope. So how might Sky and Telescope readers and practitioners be able to participate in an FRB adventure?
Yeah, so I was attending the IAU conference in Korea virtually this year, and there was a really nice talk where people were talking about how citizen science can be developed for this field. For example, there are so many false candidates and candidates in general that we get from these telescopes.
Cool.
And right now people are doing machine learnings, but that's where the amateur astronomers who are really interested in studying radio signals can help. They can't they in addition to searching for FRBs, if they like, they can also, like, because we have so much radio interference as well. So if someone is interested in exploring what type of radio interferences can be produced at different telescope sites, in addition to searching for astrophysical signal, that will be great help. So I think there are many such opportunities which are already started to roll, which can involve a lot of amateur astronomers to do this kind of stuff.
Yeah, very cool. Very cool. Yeah, I can see all kinds of citizen science projects, analyzing the data, searching for a signal, kind of like a SETI almost in that regard. But yeah, that's very cool. Very cool. And that I think is going to take us to this very awesome Sky and Telescope article on fast radio bursts hit prime time. And Shivani, take us away.
Yeah, so the picture that you see is actually done by my very close friend Daniela, and this is the image of the very first detection of an FRB using the LOFAR telescope. And this was the first time that one of the repeating bursts was actually caught at low frequencies as 110 megahertz. So she did the illustration of that, and I see this illustration everywhere now. So I think it's becoming like more famous.
It's beautiful.
But yeah, in general, I wrote this article just to familiarize people about what's going on in the field of FRBs. So here, what I described in the introduction is basically how I got involved in the field in the first place. So it's not written in the article, but I'll tell you a backstory that I was recruited to just do a radio imaging survey of the sky to find transients. But then at some point, we decided that the telescope that we were trying to refurbish was the Molonglo Radio Telescope. So I was involved in a group in Australia. So we thought that we didn't reach the sensitivity to actually achieve that kind of sensitivity level to do our surveys. So then at some point in my PhD, we were just like, okay, what should I do? Because I was hired to make radio images of the sky to find transients. And turns out people have already done that. And it's it's not a way to actually redo it once somebody has done it better. So that's how I got involved into fast radio bursts. It's like, so as I say in the article, the very first fast radio burst was discovered by Duncan Lorimer's student, David. And this whole group was basically at Swinburne. So when they were doing it, they were analyzing Parkes radio telescope data, which was looking basically for pulsars in the direction of small Magellanic Cloud. So Matthew Bales, who was my supervisor, he told me this story, and I was like, wow, I would really like to study these mysterious bursts, because these are not coming from our galaxy that was established from the very first Duncan Lorimer's science paper, because they had something called dispersion measure, which was for these bursts higher than what we expect from our own Milky Way. So that kind of hinted that these bursts are something which are not created in our own galaxy, but are coming from far away. So I can maybe briefly discuss what dispersion measure is, because that's the most important property of this FRBs that help us to do this all awesome cosmology that you will find later in the article. So dispersion measure it's like a proxy for distance. It's like the integrated column density of free electrons along us on Earth and the source which is emitting the burst. So it actually tells you how many free electrons the burst signal has encountered on their way from their source to Earth. So it's also a proxy for distance. So if you look away from the galaxy, these bursts are coming with higher dispersion measures. So using the various pulsars in our own galaxy, people have modeled along a given line of sight how much dispersion measure you expect. And when you look and when you find these FRBs coming from those directions, there is so much extra dispersion measure that our galaxy cannot contribute to. So that tells us that these are the bursts which are coming like halfway across the universe. And it's like a blueprint of everything that it's going through when it starts from its host galaxy to when it reaches us. So the whole medium. So that's why that's the best thing I like about FRBs, just because of this very, property of dispersion measure, where the electrons, the low frequency electrons get scattered and they arrived at the telescope later than the high frequency electrons. And if you scroll up, you might see a plot of the dispersive sweep for the Lorimer burst. So that dispersive sweep is actually what enables you to tell what FRB has gone through when it traveled from where it originated to when it came and we detected through our telescopes here on Earth.
Cool. Very cool. So what do we got here? This is this one's a broadband.
Yes. So here you don't see the sweep because we have corrected for the time delay. So as I explained that the higher frequency electrons are reaching our telescopes first and low frequency follow them. So there is a sweep. But when you correct for the delay, you try to straighten out that pulse, and that's what you see in these plots. So here the effect of the dispersion has been taken out, and that's how you see the pulse, and the signal that you see is the broadband signal, because as you can see, it shines over the entire frequency band that we are observing. And we live in a world where we have these really awesome telescopes, for example, CHIME and ASCAP, which are finding so many of these bursts. And CHIME has just like, those are the cylindrical paraboloids, and they have almost taken up the field of finding FRBs, because they are finding like 1 or 2 FRBs every day. It's like raining FRBs at CHIME in Canada. So yeah.
Very cool. Very good.
Yes. Yeah. So and the plots that you see here now, because we have so many of these bursts, we can actually start looking at the morphologies and try to categorize them into various categories. And these are the 4 categories that we have so far. So the first, as I explained, is a broadband because it's shining across the whole frequency. Second is a narrow band, because you see the emission is just constrained to in frequency and it's not shining across the whole band. And then you have these more complex bursts where you see these double peaky structures in the profile as well. And then the last category that we can see is this sad trombone effect, which is a very funny word, but it's a sad trombone because it's like, pom, 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 pom. Exactly. So it's like marching down of frequency with respect to time.
Got it.
So,
Okay. Yeah, very cool.
So the very special thing about this sad trombone effect is like, so when we initially found FRB, we just saw one burst coming from the same location in the sky at a same dispersion measure. And then we kept on staring it with Parkes and ASCAP, but we didn't see it repeat itself. But then there was one fast radio burst, which completely, it was a breakthrough in the discovery of this whole field, which actually started repeating itself. So it's called famous 121102 or R1, because this is the very first repeating FRB which was detected. So this burst was originally detected with Arecibo, but then when people start to look at the same patch of the sky, they actually started seeing the burst repeat itself. So this was the very first evidence that FRBs can also repeat, because all the bursts that we have seen so far before 2017, just like, bang, something happens, you detect a pulse, you see a signal, and then nothing. And hundreds of hours of looking at the same patch of the sky and nothing. And then that gave rise to different theoretical models, like this could be like, catastrophic events, like two merging compact objects, merging neutron stars, or these crazy ideas like supermassive black holes and stuff like that, because this all seems so explosive and catastrophic, right? Yeah. But then when the repeating FRBs were yeah, exactly. So, but when the repeating FRBs were discovered, then we realized that, oh wait, not all FRBs need to be catastrophic, because if the source is repeating the burst, if the burst is being seen in multiple times from the same source, which means that the source hasn't destroyed itself. So there must be some other theory. So then these 2 speculative classes of fast radio burst, one we call them one-off burst, very extreme burst, high energy, and then the other category is the repeating burst, which are not as bright as the one-off burst, but they are repeating themselves. And interestingly, these repeats are not like the repeats of a pulsar, which are very periodic in nature. These are very random. So we haven't seen any patterns in the repetitions of these emissions from repeating FRB sources. This is very aperiodic. It's opposite to what we know about pulsars and their repetition. So in that case, it's very different. So coming back to the sad trombone effect, so the repeating FRBs are the bursts that we have seen so far that show this sad trombone effect. And the sad trombone effect has not been seen for any of the non-repeating ones. So this kind of hints towards like there is something very exotic happening in the magnetosphere if it's a compact object, or some sort of emission mechanism that's only the source which repeat itself can produce this type of sat trombone effect that has not been seen for one-off FRBs. Yeah, so if I show you a gallery of all these beautiful FRBs and you see sat trombone effect, you can say, I know that one's repeating, or it's going to repeat at some point.
Very good. Very good. And this is something like a citizen science project could be doing. Once this data is downloaded, once you do the subtraction or the adjustment for the dispersion measure, and then you start looking for these different types of signals. So yeah. Citizen science projects there. Very cool.
Yeah, and then we talked about chime, and then I write about getting closer or getting personal with FRBs, because earlier when we were finding these sources, let's say with Parkes, the localization region was like half of the size of the moon. So and it was very hard to pinpoint which galaxy is producing the burst or which galaxy is the host of the FRB. But when interferometers come into play, like VLA or ASCAP, then you can actually make an image, and in the image you can see the FRB and you can localize it. So that was the beauty of finding or localizing FRBs with ASCAP. Like, for example, in this particular burst, we knew that the FRB was coming from the galaxy. We could point out this host galaxy, which we haven't done before. So now once we know which galaxy is producing FRB, we can really zoom in to that galaxy and study in, like, with Hubble Space Telescope or with very high resolution, high spatial resolution, and actually see and actually try to study the local environment of the FRB itself.
Cool.
Yeah, so that was why I say getting personal with FRBs, because previously we just know, a burst happened, but now we can actually, trying to see like who's living in the home. We know the home address, we know the telephone number, just like trying to see what source is this.
That is personal. Once you know the address, it's personal.
Yeah.
Very cool.
Yeah, and then we were finding FRBs in Milky Way type galaxies, like in the galaxies which have those properties similar to our own galaxies. But then something very exciting happened. We found an FRB in a globular cluster, which was very surprising, because initially we thought that like you will find, or you can generate the source of FRBs in a very highly star forming regions, because in those star forming regions, new stars will born, they will explode, and then the remnants could be a magnetar or a neutron star, which could produce an FRB. But there is no star formation happening in globular clusters, because they are like stellar graveyards, and nothing's going on there. But then the authors of this paper, they put forward an idea of there might be more ways of, creating a magnetar rather than a core collapse supernova or a big explosion of a star. And that could be collisions of two white dwarf stars, because white dwarf are like very old stellar population, very old stars, and places like globular cluster are full of them. So it could be a different scenario in which a progenitor was born, which is now producing these repeating bursts. So that was a really exciting find, very different from what we have expected, given all the locations that we know where FRBs are coming from and what type of galaxies they are coming from.
Speaking of, do you ever find two FRBs in the same galaxy?
We haven't seen so far.
Okay.
So in the same galaxy, two FRBs, if it's repeating, yes, then the same source can emit repeating bursts.
Sure.
But we haven't found two different FRBs from the same galaxy. Yeah.
Okay.
Yeah. Yeah, and the other thing that I would really like to highlight in this article was this FRB-like signal that was detected from a magnetar in our own Milky Way. That was another breakthrough result, because we were searching for all the FRBs in like all over the sky, and then something exciting happened in our own Milky Way, which turned out to be coming from a SGR, which is like soft gamma ray repeater. It's a magnetar source, 1935. So here you go. So maybe some magnetars can also produce a population of FRBs. So that is a very leading model as well. So yeah, and now there are so many different programs coming up to actually find more FRBs in our own galaxies and yeah, do amazing things with them. Yeah.
Yeah. Very well. There's probably several progenitor channels.
Yeah, so what I think FRBs can be produced in more than one way, definitely,
Mhm.
because yeah, one could be magnetars, yes, sure, magnetars and their magnetic fields, all the crazy stuff happening in the magnetospheres, and other could be another more exotic, like colliding compact objects or a neutron star or a black hole or something like that. Yeah. Mm.
Got a nice little illustration here of what happens on a compact
Yeah,
object.
yeah, so this illustration is like if FRBs are coming from magnetars, then there could be another two scenarios. One is the FRB is produced inside the magnetosphere of the magnetar, in which case you see the FRB here, yeah.
Okay.
And on the figure next to it, the FRB could be produced from the shock when the burst, when you know the ejecta hits the ambient medium. So that is because of the relativistic shock outside the magnetosphere. So those are the two scenarios in which FRBs, if they are coming from magnetars, can be produced like that. Yeah. I found this very cool. Yeah, this illustration, I really like it.
Yeah, very good. Very good. Is this an S&T illustration?
So this was illustration in like one of the papers from Bing Zhang. So
Okay.
and then SNT quoted and gave credits to them. Yeah.
Very nice. Very
Mm.
cool. All right. Cosmology probes. Ooh.
Yeah, and that's how I mentioned, like, because of this awesome dispersion measure, FRBs are like blueprints of they have like signatures of what they are passing through. So we could study the intergalactic medium, their densities, the magnetic fields, and all those things. I know it has been done using different methods, but the beauty of FRBs is that FRBs can provide an independent measurement of what we actually know, and we can cross-check whether what we know about the universe is correct, or FRBs or you know, it's completely different and we were missing something. So that is another way to check what we know about, like, for example, missing baryons, which is a very a hot topic in the field of cosmology. It's like, okay, we know 70% of our energy is dark energy, 25 is dark matter, and what we know about is like only 5% of baryonic matter, like normal atoms and stuff that people are made up of. And of that 5%, we know 50% people have found it in galaxies, but the rest of that baryonic matter is missing. And people think it could be in the, you know, warm, hot intergalactic medium. And FRBs pierce through those mediums and they could tell you exactly about where these missing baryons are. And that's actually being done for the very first sample of localized FRBs with ASCAP. And I was really excited to be a part of that study. Yeah.
Yes.
And then, and
Fantastic.
this beautiful telescope is finding and localizing FRBs and yeah. So when I grew up, I was so interested. I get so excited, you know, looking at Hubble images of these planetary nebulas, and now I actually got to work with the Hubble images and see the FRB galaxies. It's just like came to full circle.
Yeah, very nice. That is a full circle. Very cool. Those are kind of fun. You know, it's been happened before. You have a serendipitous accidental discovery, and then it starts telling you all kinds of things about either cosmology or compact objects or something
Yeah.
like that. But that's that serendipitous discovery of, whoa, look at this. Very
Yeah.
cool.
Yeah, I think I'm learning with FRBs myself, because earlier I used to call myself a radio astronomer who is like looking at radio data to search for these bursts. But once we started localizing them, then I'm becoming an optical astronomer. I'm studying
Ooh.
their galaxies. And now once we have a lot of FRBs, I might become a cosmologist because
Oh
I want
no.
to.
It's the inevitable evolution, let's put it that way.
I don't know, but yeah, I
Uh,
really love working on FRBs. It's a
Very
beautiful
cool.
mystery.
Yeah, oh, it's a happening field. Very cool. Well, thank you so much, Shivani, for sharing your Sky and Telescope article and aspects of the field. Very cool. So you mentioned it a couple of times, or you hinted at it a couple of times. So let me phrase it this way. So when is your next Sky and Telescope FRB article? And more to the point, where do we go from here? Are there additional facilities coming online? Maybe a square kilometer array. Is there something JWST can do, or the Nancy Roman telescope? And just sweeping back, I want to see what we can do to engage the citizen science components again. So
Yeah,
just where do we go?
As I say in my article, like the future of FRBs is as bright as they are, because once we started finding these bursts, now like all the engineers and astronomers, they're tuning their search algorithms, they're tuning their instruments so that they can search at highest time resolution to catch these bursts. And then it's not, so CHIME has already taken over that, but now the whole field revolves around we need to find and localize more FRBs, and that's where new instruments are building up. So there is a experiment called COD, which is like putting up CHIME outriggers, so that when CHIME detect the bursts, they can also localize them on milliarc second levels. So that is one project that's going on. And then there's another one with some colleagues in Caltech. It's called Deep Synoptic Array 110. And then they have got got funding for DSA 2000. So it's like 2000 dishes to catch these bursts and localize them, dedicated to FRB work. So that is also pretty exciting. ASCAP itself, that I'm a part of, we are doing a upgrade on the whole system, so that for now we were searching for FRBs in an incoherent way where we sum their power. So we lose a bit of sensitivity there, but if you search in a coherent way, you get additional boost of square root of number of antennas.
Right.
So we are upgrading the system to search for FRBs in a fast imaging coherent way, so that we are more sensitive of catching these bursts and localizing them. And LOFAR itself, that currently, which is a part of my project, is going upgrade. It's called LOFAR 2.0, which will be able to use the high band antennas and the low band antennas simultaneously. And we can have multiple beams on the sky looking at repeating FRBs and try to detect them at low FAR frequencies. So yeah, a lot more exciting things are going to happen with FRBs in the future for sure. And as far as you said, citizen science is concerned, definitely, because we see there are so many morphologies of FRBs. So like it's really hard to train the computer, but human mind can easily look at the signal and can, we are excellent training algorithms. So we don't need
patterns.
We are excellent as identifying patterns, and especially with these upcoming facilities, we're going to have so much data, so many candidates to go through before we can actually learn our computers. We need to have a good training data set for our computer to learn. So for that training data set, I think citizen science can come up and they can have a look at the candidates themselves and categorize them, so that information can be fed to all these computers, which can make our job more easier than going through individual looking at these candidates. Because there's going to be so much data in the coming future, like with the ASCAP and LOFAR and MeerKAT and also SKA down the horizon. There's so many opportunities to get involved with this kind of categorizing FRB signals. Yeah.
There's discoveries to be made.
Yeah, exactly.
And so
this is all like
can help make those discoveries.
Yes, exactly. It is all very serendipitous. So yeah, maybe they'll find some different kind of FRB that we haven't seen so far. Like, for example, right now our searches are limited to few milliseconds, but they can come up and they can expand, have a search at a broad, like for seconds or for hundreds of milliseconds. So it will so it will be like searching up in a different space. So they could also maybe discover slow fast radio bursts, for example. So yeah.
Then we need a new acronym, because slow fast doesn't work for me. Awesome. Very cool. Very cool. Well, I look forward to seeing your second Sky and Telescope article here in a year or so, and we'll see where we are on all this activity. It's very cool.
Thanks, Frank.
Shivani, thank you so much for walking us through your very lovely article.
Thanks. Lovely to be here and talk to you. And yeah, it's been great. Yeah.
And that will do, everyone. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.